This exact exam response is a complete, devastating zero-mark disaster that probably looks entirely reasonable to half the students taking the Cambridge IGCSE physics exam. We're talking specifically about the 0625 Forces and Practical Skills paper. If you've ever walked out of an exam hall feeling like you absolutely crushed the physics, but then you just bleed marks when the results actually come out, this is exactly why.
Now, if you're just chatting with a friend saying, the spring stretched more because the weight is heavy, makes total sense, right? Intuitively, it's true. But to a Cambridge examiner, that instantly loses all your marks. It gets a 0 because it completely lacks the specific terminology they are hunting for. It's such a painful learner mistake because you clearly understand the real-world physics, but you just aren't speaking the mark scheme's language.
So, stop revising by just passively reading your textbook over and over. Seriously, it wastes your time. Ordinary textbook reading completely fails to secure top bands in Cambridge practical questions. Why? Because knowing the background theory and knowing exactly how to extract marks from an investigation question are two entirely different skill sets. You can memorize facts about springs all day long, but if you don't know the precise traps they set in these practical papers, your grade is going to hit a rigid ceiling.
Instead, we literally need to reprogram how you answer these questions. I call this the mark magnet framework. It essentially forces your brain directly into mark scheme alignment. Whenever you face a describe, explain, or evaluate question, you absolutely must move through these 4 exact steps. First, state the scientific concept. Second, pull exact evidence or data from the prompt. Third, provide the scientific reasoning that links them together. And fourth, wrap the whole thing in exact examiner wording.
Now, lock this framework in your mind right now. In a moment, I'll show you the exact examiner clue, a specific graph axis error that changes the answer completely and destroys top band scores. Leaving now means missing the key examiner clue that changes everything. But first, you really need the framework that makes that clue totally obvious.
Okay, let's dive into this and apply the mark magnet framework directly to a classic Cambridge practical setup. We're talking about stretching a spring to test Hooke's law. This is easily one of the most frequently tested practicals in the entire 0625 syllabus, so you really need to know this inside and out.
Take a really close look at this experimental data table. We've got load in newtons on the left and extension on the right. I want you to actively engage with this for a second. Play examiner. Spot what is missing here. What critical piece of information has this student completely forgotten that is going to instantly cost them a formatting mark?
Did you catch it? The unit for extension was totally missing. This brilliantly illustrates one of the absolute most common data traps. You must put the unit, like millimeters or centimeters, right up in the header, not written next to every single number down the table. Other massive traps to watch out for? Round in your calculations way too early, which just causes compounding errors later on. Giving vague explanations of trends instead of stating direct proportionalities. And of course, completely ignoring data anomalies. Speaking of anomalies, let's test your eyes one more time. Look back at the progression of our data here. 1 newton gives an extension of 5.1, 2 gives 10.0, 3 gives 15.2, and then suddenly 4 newtons jumps to a massive extension of 28.5 before 5 newtons actually drops back down to 25.0. That 4.0 newton reading is clearly an anomaly, but how do you actually write about it on the exam without losing marks?
This is where the mark magnet framework transforms a flawed response into a top band answer. Just saying data point 4 is wrong earns absolutely 0 marks for evaluation. But stating the 4.0 end load produced an anomalous extension of 28.5 millimeters deviating from the linear trend provides the concept, the exact data evidence, the reasoning, and that perfect examiner wording. That right there is how you literally pull marks from the examiner.
So the absolutely crucial point is knowing the exact scientific concept before you even think about plugging in your reliable data points. The spring constant, represented by a lowercase k, is strictly defined as the force per unit extension. The equation is k equals F divided by x. Physically, it represents the stiffness of the spring. If Cambridge asks you to define it, use this exact wording. Don't just casually say, it shows how stretchy the spring is.
All right, let's move to something a bit trickier and see how this builds. We are escalating the stakes to moments and center of gravity. The practical investigations for this topic are notorious for stripping marks from underprepared students because the setups require absolute, meticulous precision.
Okay, I'm putting you back in the hot seat with another spot the error checkpoint. Take a look at this proposed method for a balancing practical investigation. Balance ruler on pivot, measure distance from center. Why does this score so incredibly poorly?
Honestly, it sounds exactly like what you casually do in the lab, right?
Well, here is the brutal, harsh reality, straight from the examiner's feedback, to demonstrate how precise your wording actually needs to be. Vague method. Fails to account for the ruler's own center of gravity or specify measuring from pivot to the center of mass of the load. You see, measured distance from center is just way too vague. Which center? You must explicitly state that you are measuring from the pivot point directly to the center of mass of the load.
To capture all the method marks for a balancing experiment, you absolutely need this exact step-by-step sequence. Step 1, find the ruler's exact center of gravity first by balancing it all by itself. Step 2, place the pivot off-center. Step 3, add a known weight. Step 4, carefully adjust its position until it's perfectly balanced horizontally. And Step 5, calculate the moments using the equation force 1 times distance 1 equals force 2 times distance 2. Always structure your answers in this exact sequence to guarantee those marks.
And this brilliantly illustrates that massive graph trap I warned you about earlier. This right here is the axis error that will instantly cap your grade. Look at this cramped scale. It barely uses any of the page, and it completely misses the 0-0 origin. For top ends, your graph must literally take up more than 50% of the provided grid. The axes must be distinctly labeled with both the quantity and the unit, like force/n, and your line of best fit has to be clear, balanced, and sharp.
Okay, before you even think about finishing any practical question, run through these quick final checks to secure those last accuracy and reliability marks, even when you're under extreme exam timing pressure. Check that your units match standard SI units. Check that your significant figures strictly match the precision of the raw data they gave you. State any experimental uncertainties, like avoiding parallax error when you're reading a ruler. And list highly specific safety precautions, like wearing safety goggles to protect your eyes from a snapping spring under high tension.
Now, everything we've covered in this explainer so far is going to drastically pull up your marks. You've got the mark magnet framework now. You know exactly how to structure your methods and plot your graphs perfectly. But there is a fatal data evaluation trap we haven't solved yet. It's a trap that constantly trips up the conclusions for even the most highly prepared A-star students.
Think about this curiosity gap for just a second. Hooke's law dictates direct proportionality, right? We know this. But what happens when you plot your perfect graph, you draw your beautiful line of best fit, and it absolutely does not go through the origin? The theoretical law says it must. Your experimental data is screaming that it doesn't. How do you evaluate that in your final exam conclusion without losing everything?
You simply cannot walk into that exam hall without knowing how to handle that exact scenario. You need to master the top band evaluation framework. The good news? We have even more mark magnets waiting for you, covering exactly what to write when your data defies the theoretical law, and it's right in our next explainer. Framing your conclusions correctly is an absolute necessity if you want the top grade.
Click the explainer on your screen right now to solve this exact evaluation trap once and for all. And make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE, to excel in your Cambridge examinations. Let's keep building that bulletproof mark scheme thinking. Click over, and I'll see you in the next explainer.